Hi there, my name is Rajat Paharia, and I was recently asked to give a presentation on demystifying generative AI at the University of Arkansas at the invitation of the Office of Entrepreneurship and Innovation there. Now, unfortunately, the recording there, you couldn't see any of the slides, so I'm re-recording it here, doing a dramatic reenactment. By way of background, I'm currently the founder and flounder at Ask Steve, which is time-saving AI agents for your browser. You can learn more at asksteve.to. Prior to that, I was at Google for 8 years as a product manager, where I worked on smart home devices, maps for real-world game developers like Pokemon Go, augmented reality on phones and glasses, and ended my tenure there working on internal HR technology for their 180,000 plus employees. Before that, I was the founder of a venture-backed startup that created the gamification industry, worked for a company called IDEO, product design and innovation firm, for many years, and then was a software engineer before that. Now, generative AI often seems like magic, right? The fact that it can create outputs, whether it's text, image, audio, video, that seem like they were created by humans. And so today, the goal is to show you how the magic trick is done for a couple of reasons. One is the better you know your tools, the better you are at using them. So you having an understanding of what's actually happening, I think, can make you a better user of these tools, a better informed user of these tools. But then also to talk a little bit about kind of if you zoom out and the bigger context in the world that these things live in and how we should be thinking about them as we use them. So that's going to be the goal. And so let's just dive right in with how it works. So I want you to fill in the blank. I'm giving you one word of context, two, and asking you to predict what the next word is going to be, or guess what the next word is going to be. Now, you know, what's happening in your brain right now? Like, it's basically feeding this word two into your brain, and your brain is looking through all the data that it has. And this is everything you've ever read, heard, said, thought, been exposed to, everything. And it's kind of filtering through that whole data set, trying to find a pattern that it can match to give you what the next word is here. And you're probably coming up with like not a whole lot or too much. Basically, like even the not a whole lot is basically because you're coming up with too much. You're getting like an infinite number of low probability answers here because this isn't enough context for you to predict what the next word should be. So now let me give you one more word. And all of a sudden, it's going through that same exact process again of going through all your, let's call it your training data, which is all the content that you've absorbed over the course of your lifetime. And now it's got kind of a high probability match. You think you know what the next word here is going to be. Now, it could be, you know, you don't know. The sentence, my son Evan just had a birthday on Sunday, and it could be, I want Evan's birthday to rock, right? So the word could be rock. But you do have a list of potential words in your head, and you've got one that's probably very high probability that's a match, and that's because it's something that you've heard over and over again during the course of your life. And if I give you one more word of context, you are like probably 99.99%, if not 100% sure what that word is. So now with one word of context, you couldn't figure it out. With two words, you had a high probability prediction, and with three words, you've got like almost a guarantee that you know that the word is you. So what actually happened in your brain? Your brain is composed of around 120 million neurons, and the long skinny part here is called an axon, and it connects to other neurons at these things called synapses, which is the spaces between the end of the axon and the dendrites of the other neuron. And every single neuron can have like 10,000 plus of these dendrites. And so you've got this big, effectively mesh network of neurons in your brain that are all connected to each other. And every time you learn something, the strength between some subset of neurons gets stronger or weaker. And encoded in all that data is everything that you've learned. Like everything that you know, everything you learn is encoded in these synapses between these neurons. So when I learn something new, like that the word hola in Spanish means hello, like all of a sudden some connections between some neurons get stronger. And so happy birthday to you. That's something you've heard probably, you know, thousands of times over the course of your lifetime. And so those neurons for that particular pattern are really strong. And so that's why when you saw the word birthday, it kind of lit up, and happy birthday, like kaboom, like you actually you knew what was happening. So this is how the human brain works. Now, in the world of AI, there were two schools of thought back in the day. There was a school of thought of top-down AI, which is that intelligence comes from knowing things. And the way you know things is you tell the program all the facts in the world, and all the symbols, and then you give it like the tools to manipulate those symbols. So, man eats banana. Banana has peel. Does man eat things that have peels? Yes, because you can kind of go across those symbols and figure that out. The problem with this is, how do you encode all the facts in the world, right? Like, maybe this works for a very small domain where you can quote unquote, know all the facts and the relationships between all the symbols and the objects. But for just general purpose intelligence, like, this doesn't scale. It's like really hard. The other school of thought was bottoms up AI, which is that intelligence comes from learning, and what we should be doing is simulating what happens in an actual brain. Build an artificial version of that thing we just showed, the neurons in the brain and the synapses, an artificial neural network. And now the problems in the early days of neural networks was a lack of data for training these neural networks, a lack of compute for doing that training, and then really inefficient algorithms for training those networks. And so for a long time, these two were kind of in competition with each other. And if we look at the history of neural networks, the very first model of a neural network happened in 1943, like a really long time ago. And then, not a whole lot kind of happened until 1969, when the top-down AI guys kind of stuck a knife into the side of the learning guys, and then learning just kind of like went into a winter, long dark period for many years. And then I think there's a couple other things that happened, but the big events that kind of happened that are of interest to us happened in 2012 and 2017. So in 2012, a software system called AlexNet won a competition called ImageNet. And what ImageNet was a database of images that were annotated with labels that had been created by a professor named Fei-Fei Li, because she believed that like large data was going to be important for figuring these things out. And so she curated this giant data set and ran this competition every year, starting in, I think, 2009. At least that's when the data set appeared, but somewhere between there and 2012, she started the competition. And every year, people would compete to see like who could do the best at image recognition on this big corpus of data that she had created. And in 2012, AlexNet, a neural network, won and kind of beat the state of the art by a great deal. And so all of a sudden, that kind of breathed new life into the world of neural networks. And so how does this work? What's a neural network look like? And this is from a great video by the YouTube channel 3 Blue 1 Brown. So let's say you're trying to recognize the handwritten numbers that somebody is writing somewhere. And so you take an image of the number that the person wrote, and it's a 28 by 28 pixel image, and you feed it into a neural network. So every one of those pixels in this image gets turned into an input neuron in this neural network, which we'll see here in a second in the image. And if it's filled in with a color, with white, then its value is 1. And if it's not filled in, then its value is 0. If it's something in between, it's got a partial value. And so all these neurons have some number value in them. And what we're trying to get at the output is the neural network to tell us, what number is this? And so we want it to light up one of those neurons. And so what I'm actually going to get out this end is 10 different probabilities of what that number could be. And so hopefully for this particular one, I'll get like 100% on number 9 and like 0% on all the rest. But you can see how, like, if the model wasn't really sure if it was, say, a 1 or a 7, I might get a 50 there and a 50 there. All the probabilities should add up to 1. And so this is basically a distribution of its confidence level of what that number is. Now, in the middle are what are called hidden layers. And these are the layers where kind of the quote unquote learning and thinking happens. And so this is an example of what like these layers might do. This first layer here might identify little pieces in the image. And those little pieces then can fire off to the next layer, which then identifies bigger pieces, like a loop and a line. And then based on which ones of those light up, that's how the model can tell what number is actually in the image. So it's kind of magic, right? Like if you imagine what it would take to write a program without a neural network to figure out, like, let's say, is this picture of a cat or not a cat? Or like in the previous example, what handwritten number is here? How would you even do it? Like, You're going to look at all the pixels in the image and then do what? Like if there's an eye, eyes could be anywhere in the picture, fur could be anywhere in the picture, ears could be anywhere in the picture. There kind of like is no good way of doing that. And that's the kind of thing that neural networks are really good at and are amazing at. So in this particular example, we're looking at a neural network that identifies whether something is a cat or not. And so we have one output, is this a cat? Yes or no. And on the input, we have very similar to the last example, every pixel of the image is a neuron. So there'll be a lot more than this actually. So you feed in a picture of the cat, it goes through these hidden layers. These hidden layers are identifying things like, is this a line, an eye, a nose, a fur, triangle, an ear? And then it goes through the hidden layers and it comes out with a verdict. Is this a cat or not? Now, how does this get trained? And very similarly, how does the previous network we looked at get trained? Well, the way it gets trained is, and I'm going to simplify this a bit, but you feed in a picture of a cat. And at the very beginning, this neural network, all these connections between neurons, which are kind of the equivalent of the synapses in the brain, have a strength of connection to them. And the same way that synapses get stronger and weaker as you learn things and forget things and learn new things, then these things get stronger and weaker as well when you're training. So at the very beginning, all the weights here, all the strength of all the connections is basically random. So the network is garbage. Like you will feed in images and you will get effectively random answers. But what you do then is I feed in a picture that I know is a cat because it's labeled as cat. It goes through the whole thing. And if the answer is yes, that's good. And I just keep going. But if the answer is no, then what I do is I go back and I adjust the weights in the network to get me a yes answer for that particular image of a cat. And then I do it again and again and again with a bunch of different images, including not cats. And over time, as I'm continuously adjusting these weights, the network is quote unquote learning about all these various features. I'm not telling it that it needs to look for these things. It's kind of figuring it out. These neurons are each kind of specializing and identifying certain areas. And then overall now, this network, when it's all trained and done, it should be able to take my entire training data set. And if I feed it through, I should get all the accurate predictions. And then the way I test this network is I take some new images that it's never seen and I feed it through and I see how good it's doing. And then I continue to train if I need to. And so basically what you're doing when you're training a neural network is just adjusting. These are called the parameters or the weights and biases in this neural network between all these neurons to make it an accurate reflection of the training data that went in so that it can correctly give you the yes or no answer. And this isn't always easy, right? Like this kind of famous image of chihuahuas and muffins, like you can see how even humans might struggle with some of these images. So how does this relate to generative AI? Okay, so now that was 2012. AlexNet kind of showed that neural networks could be used for image recognition and do way better than all kind of the state of the art stuff. And now we get to 2017 when a bunch of Google engineers and researchers that were working on machine translation invented something called the transformer. Now, until then, kind of the state of the art had been what was called recurrent neural networks. And the idea was to look at each word in sequence to kind of figure out the next word, the meaning of the next word, so that you could do the translation. And so you go I, and then have, no, interest. But you can see here that when you're doing this, that let's say we don't see these last two words yet. By the time we get to the word interest, this could mean interest as in affinity for something, but it could also mean interest as in like the dividend on my bank account. And you don't know at that point in time. And so then all of a sudden my translation can take a left turn that goes in the wrong direction. So, and this graphic is taken from a really great free article that you can access from the Financial Times called Generative AI Exists Because of the Transformer. So what was the innovation of the transformer? It was to look at all the words at the same time and to be able to figure out which ones for any particular word, which other words in the surroundings are the most impactful to its meaning, so that you can then say, like in a sentence like this, know that the first interest is more about kind of affinity and the second interest is more about dividends. And so that was the big innovation of 2017. Why the name Transformer? Apparently because it sounded cool to one of the people on the team. There were 8 people that wrote this famous paper called Attention is All You Need. They published this to the world. And again, the intent had always been about translation, but then they realized that this could be used to generate content. And now Google didn't do a ton with this publicly. Like, I was at Google at the time. They had internal large language models, one called Mina, one called Lambda. But OpenAI took this and started shipping products out into the world. GPT 1, 2, 3, 3.5. And so you can see here that for like 4 years, they were shipping all this stuff out into the world, and the world was kind of yawning and they didn't care. And then when they put a chat interface in front of it in November 2022 and launched it, all of a sudden, kaboom, and that launched us to where we are today, right? With like the generative AI boom. So what does GPT stand for? This acronym that like we all now use multiple times a day, probably. Generative, it can create things. It's not just for analysis or summarization or training. It can create new content. Pre-trained means it's been given a whole bunch of data to start with, the same way that you have been pre-trained on like everything you've ever experienced in your lifetime. And then the transformer, the name of this particular technology. So let's go into the pre-training. How does this happen? And a bunch of the next couple of slides are kind of taken or modified and adapted from a really great presentation by Andre Karpathy called Deep Dive into LLMs, like ChatGPT, that's on YouTube. 3.5 hours, well worth like kind of the deep dive to understand how this stuff really works. But the first thing you need to do is you need to get the big data set that you're going to train your large language model on. So you want to crawl the internet, and you either do it yourself or use somebody else's crawl, like the common crawl. You decide kind of what you want to, if you're crawling it yourself, you're going to decide what you want to get. You do some URL filtering, you do some text extraction to just get the raw text that you want. And then you kind of do deduplication and filtering. So if you only want English language, then you filter out all the other languages, etc. Okay, then you have this giant corpus of textual data. And what you do is you turn it into tokens. And if you see the link here, you can click on this and go put in any text you want. You can see how it gets tokenized. So these large language models work on these things called tokens, and they don't work on words. They don't work on letters. And which is interesting. It's the way that the tokenization works is you're trying to strike a balance between the size of the vocabulary that you're dealing with and the length of the sequences that you're dealing with. And so as an example, let's say I made one token for every letter in the English language. Then I'd only have 26 tokens, which is great. But my sequences would be super long because I would be a token, N would be a token, space would be a token, E, S. I'd have very long sequences, which would be too much compute. On the other hand, if I use the English language, which has 1 million words, then my vocabulary is giant and my sequence lengths get smaller. But that, again, is like too much compute. It's too far along one side. And so there's kind of some balance here of how many tokens you want and sequence length. And so if we look at GPT-4, that had 100,277 distinct tokens in its vocabulary. So what happens is you have some text. Here's some text from an article. And when that text gets turned into tokens, and we can see here that a lot of these tokens are space followed by a word, or just the word, or you can see that there's, in some of the places, you'll see parts of words, like ChatGPT is actually 3 tokens right here. And so all of these tokens are generated from your text. And this is the text representation of the token. But then every one of those tokens has an assigned ID or value. And this is what that looks like. And so we can see here that the word this is 2028. Analogy is 56203, makes is 3727, even is 1524. And this is what large language models work on, this token representation. So they don't see letters, they don't see words, they don't see sentences, they don't see paragraphs. All they see is these sequences of numbers, these tokens. So then, how do you train the large language model to predict what the next token is going to be? Because that's what we want it to do. We want to predict. Well, you grab these what are called context windows. And these windows can be of variable sizes, starting from 0 and going up to some maximum amount that, again, there's like a way to decide kind of like what a good amount is for the amount of compute that you have available. In this case, early LLMs started with like 1K, 8K, 32K. They're now up to like 1 million and 2 million token context windows. So we take these context windows of various lengths, and then we go process them. And so for this example, we're going to take these first 4 tokens. This analogy makes even. So we have those tokens, and these are the actual tokens that the large language model sees, and then these are the words they represent. We then feed that through our neural network. Now remember, our neural network is initialized initially with like random values, so we're probably going to get kind of garbage out. What we're actually going to get out is we have our whole vocabulary of tokens, the same way that we had 0 through 9 in that number example. In this case, we're going to have all 100,277 tokens. And for each one, we're going to have a probability. And all those probabilities together are going to add up to 100%. Now, we can see here that if I feed this particular sequence of tokens, these 4, into the neural network, it's going to say, hey, okay, the probability of the word the is 5%, and less is 3%, and more is 2%. But in this case, for training, we actually know, like, well, this is where we grabbed this context window from. We know exactly what the next token is. It's 810. So we want to go back and tell the network, hey, adjust your parameters, your weights and biases in there, so that 810 is a higher probability and the others are lower probability. And then you go back and you grab another window of tokens, and you do it again, and you do it again, and you do it again with various solid windows, and over and over and over again. This is the training process, and so it's kind of very similar to here. And at the end of the day, you've adjusted the weights and adjusted the weights, and now you have a model that has been trained on all this data, pre-trained on all this data, to be a statistical representation of all that data that you can now use to predict with new photos, whether they are cats or dogs, or in the case of the words, predict what the next token should be. So one phrase you may hear, we talked about parameters and weights and biases. You'll often see these on open source models. You'll see the number of parameters. And this basically is those weights and biases, that's a representation of the capacity to learn and represent more complex relationships. The trade-off is that you need more compute, more energy, and longer training times, the more parameters you have. And so the kind of closed source models these days are supposedly have low trillions of parameters. The open source model DeepSeek v3 at this point in time has 671 billion parameters. These are all the knobs that you can tweak in order to make this mathematical model a more accurate representation of the data that you're feeding into it. So, like, just to hammer this point home, what is that neural network? It's a mathematical model that you give it some inputs, in this case, a sequence of tokens, and based on its training data, it predicts what that next token should be. And the better it is at representing the data that it was trained on, the better the model is. Okay, so there are these things called the scaling laws that people determined, which is that the models get better when you increase the number of parameters, the number of knobs that we can turn, which is effectively kind of a proxy for the model size, the amount of data that you train on, so the data set size. So remember back when we were talking about ImageNet and AlexNet, Fei-Fei Li was the professor who was like, we need a big annotated data set of images that's going to unlock something here. She didn't know what at the time, but it did actually unlock neural networks. And now all these companies with models are training on the entire internet if they can. And then compute capability. We talked about all those training runs where you're taking like a context window and you're feeding it through and you're looking to see, does my next token prediction match what's actually in the data set? And if it doesn't, like, update and do it again and do it again, do it again. You need compute to do that, and this costs money. And so right now, these are kind of considered the immutable scaling laws, like that. This is how things are going to get better. This is how they've gotten better to date. It's unclear whether these scaling laws will continue or whether they will ever reach some kind of like, plateau and how much better they can make models. And the cost to do these things is not trivial, right? According to both Sam Altman from OpenAI and Dario Amodei from Anthropic, it's around $1 billion to train one of these closed source frontier models right now. And they're talking about the cost going even up to like tens of billions of dollars as well. Okay, so once you've done the pre-training, you now have a model that's really good at predicting the next token based on everything it was trained on, which is typically like the internet or some variation of that. But you don't want just a token predictor. You actually want a helpful assistant. So again, these next sections are all from that great Andre Karpathy video, like highly recommend you check it out. So what do you do in order to turn this into a helpful assistant? You train it on some more stuff. And this is called supervised fine-tuning. And the stuff that you're training it on is effectively conversations between a person and an assistant to give it a lot of examples of this is how you should be interacting with people. So you can see here that this is from an open source data set where the prompter is asking, can you write a short introduction about the relevance of the term monopsony in economics? And then this is what a good assistant answer should be. And then if the prompter asks this, this is what a good assistant answer should be. And so there are hundreds and thousands of these conversations now that are being generated by real humans. And so this is a lot of like manual labor here that the model can then be trained on to make it into a helpful assistant. And so you're giving it like a problem and a solution. The other thing to note is, people often talk about how these models have various personalities, right? All the people that were upset when OpenAI kind of nerfed GPT-4 when they released GPT-5, people that are using Claude as a therapist. Like this is where that comes from, right? Like they're all trained on the same kind of internet data set of stuff. Then like, how do you give your own model personality? Like that personality comes through in all these hundreds of thousands of examples of how the assistant should be responding to you. So this is where they can add their own kind of unique personality and quirkiness and flavor to things. Now, also in post-training, we have something called reinforcement learning. And so Karpathy gives a great example here of like the chemistry textbook. So there are three like main kinds of content in this chemistry textbook. One is the exposition, which is the paragraphs explaining to you exactly like some concept or how something works. And that's kind of the equivalent of like sucking up the internet and pre-training on all that data. The second is worked problems. And so here we're giving you a problem and we're walking through the solution and showing you the solution. And so giving you all the steps here. And so this is what we just saw with the supervised fine tuning. Here's the problem and here's a demonstrated solution. And we want you to imitate this. And then the third kind of thing you want to do is the practice problems in the book, where they give you a problem. They don't walk you through the answer, but there's an answer key in the back. And so what we want you to do is take this problem, try a bunch of ways to solve it, and then learn from that. And so here is an example of you're giving the model a prompt. Emily buys 3 apples and 2 oranges. Each orange costs $2. The total cost of all the fruit is $13. What's the cost of each apple? So it's going to come up with a bunch of solutions, in this case 15, and 4 of them are correct and the other 11 are wrong. And so what do we want to do? We want the model to learn from this. And so we say, okay, the wrong ones took you down a wrong path. These are not good techniques for solving this problem, but these other ones are good. So we're going to take just these 4, or maybe even just the best one, if there's some way of evaluating the best one, and then just train on those. And then just repeat this over and over and over again until the model learns the best strategies for solving different kinds of problems. And so this is very good in verifiable domains, by which we mean there is an answer, a known answer. In this case, the answer is 3. There is kind of no doubt there's only one answer, and it's 3 in this case. But sometimes there are not known answers, unverifiable domains. And so like this example Karpathy gives in his presentation, write a joke about a pelican. Now, this is where human feedback comes in, right? The system kind of can't evaluate the correctness of its answer itself and then do it over and over and over again, like a million times without any human involvement. In this case, you need a human to be able to judge, like, is this a good joke about a pelican? But we can't have humans doing this like a million times. That's just way too much work for humans in this system. So instead, what they do is they train a separate neural network to be kind of the simulated human that will evaluate these unverifiable domain answers. So in this case, we'll ask the model to generate 5 answers, have a human rank them. So the human's still doing some work, right? But a lot less work. So they rank all those 5 answers, and we train a separate neural network on those human scores. And then this separate simulated human neural network evaluates the correctness of the LLM answers. And so I got a clever use of neural networks to make one neural network to make another neural network better by being kind of the judge of its answers in an unverifiable domain. And then finally, we want to actually use this thing that we built. We pre-trained it, we post-trained it, we did reinforcement learning, with human feedback, supervised fine-tuning, all the things. We now have this very helpful assistant, and we want to use it to generate text and words for us. So I'm going to take I have this model now that's been pre-trained and post-trained, and I'm going to give it this token, 2028, which represents the word this. And it's going to get fed through the neural network. And that neural network now should be a fairly accurate representation, depending on how well it was trained, of all the data that was sent in. And it's going to give me a list of probabilities for what that next token should be, and it's going to pick one of them. In this case, it's the word, it's the number 56203, which corresponds to the word analogy. And so here in this sample step, it's picking one of those various elements based on their probability. And in this case, this is matching that first sentence that we had, that we kind of started this whole thing with. And we do it again. Now we feed in we feed in these two tokens, this and analogy. It goes through the machine. The machine spits out the next token, which says makes. Again, we're matching here. And then, but this time now we're going to get the token 912, which is the word no and not the word even. So because these are probabilities, there's always a probability, even if it's a 1% chance, that I will not pick one of the words in the system. Or it could be that this training data set actually has this analogy makes no sense way more than it has even more sense. And so who knows what the case is, but in any case, just know that these things are probabilities, and you will pick one of those probabilities, and it won't always be the top one. And we'll talk a little bit about how like that kind of window of what it picks works. But this is where things get very divergent, right? And this is why we talk about hallucinations in systems almost as if they're a bug, and they're not a bug. They're kind of a feature of the system. It's probabilities. And whenever you have probabilities, you are not regurgitating what you've learned. You are generating in real time based on these input tokens. You're predicting what the next one should be, and you're generating a set of probabilities, and you're picking one of those things. And that thing might not be what you expect. So those tokens that are being run through the prediction engine, it's not just what you're typing. Actually, invisibly behind the scenes, there's a bunch of stuff being added, prepended to any conversation that you're having with the assistant. And this is what's called the system prompt. What we're seeing here, and you can go look this up for yourself on GitHub, is Grok's system prompt. But every LLM, OpenAI, Anthropic, Gemini, they all have system prompts. And this is where the model makers give the models instructions about things to do and not to do, kind of guidelines for how to respond. And this is separate from any kind of fine tuning and stuff like that. This is basically just stuff being shoved into your interactions with every model. And so when we go through our token prediction system, all this is getting sent in first, and then your question about like, write me a story about a princess. And so it's going to look at that token, and then that token, and then that token, and then that token, and work its way all the way down before it gets to your text. So something to keep in mind is the system prompt, and that like what it could be kind of steering or guiding the model toward. Now, there's a number of things to know about inference here, aside from the fact that there's a system prompt. And so actually a great way to see these things is go to aistudio.google.com. Everybody can get here for free with a Google account. And this is where you can kind of see kind of some of the nitty gritty of some of these models. So let's go to a new chat, and we can see here I'm on Gemini 2.5 Flash right now, but I click here and I can see a number of their various models. And what we can see here is a couple of things. So one is we can see things like the context window. So this says the Gemini Flash latest model has a 1 million token context window. That's the amount of text I can give it that it can then run its prediction on. And bigger context windows means I can give it more context, more data, right? The same with the happy birthday to you. If I only give you one word of context, it's really hard. But if I gave you three, all of a sudden it was easier. If I'm going to ask you to like analyze a web page or a 1,000-page PDF, like you need to have a big context window to get all those tokens and be able to do something with them, or a big code base even as well. And then you can see the knowledge cutoff here. So models are pre-trained on the kind of all the data that they've hoovered up from the internet up to a specific date. And so here we can see that Gemini Flash latest, its cutoff date is January 2025. So it won't know anything after that. And so if you ask it for anything that happened like last week or yesterday, it's not going to know these things. Some other things we can look at here are the temperature. Here's some extra system instructions that you can add. This isn't the provider system prompt, but this is where you can add your own system prompt that will get added before anything. temperature, we talked about how you generate this list of probabilities of tokens that all add up to 1 at the end of the day, but you've got all these probabilities of tokens. And let's say in the happy birthday to you example, you is going to be up there in like probability wise. Let's call it like 95%. And then you're going to have a bunch of like lower ones that, who knows what those words are. Me, George, whatever. So you've got like a whole bunch of different probabilities here. You've got the number one, and then a bunch of lower ones. So the temperature indicates like how far down that stack should I go to consider things. And so if I set the temperature to 0, that basically, if we look here, it says creativity allowed in responses for temperature. If I set the temperature to 0, I'm saying no creativity. Pick the number 1 highest probability token always. And so then, therefore, you should, if I run that same request over and over and over again, I should get the exact same answer, right? Because it's just math, statistics, running on something. And if I'm saying ignore the whole probability distribution, just grab that number 1 token every time, I should get the same answer. The reality is I don't get the same answer. And there's a whole a white paper by the company Thinking Machines about like why that is, even though I should get it. And then if I set a temperature to 2, that kind of maximizes the possibility space of all the different tokens that I can pick from. And so that can lead to like then wildly divergent stuff. Like, if I'm writing a story about a princess, like the princess went to, and then if the next word is bed or Spain or, whatever, church, like all of a sudden I've got 3 like very different stories going on, right? And so the bigger the temperature, the more creativity you can get. And so you should adjust this depending on what you're trying to do. If I'm trying to summarize a web page, do I want it making stuff up? No, I want it to be very accurate and true to the web page. If I'm asking it to write marketing copy or something else, a story, do I want it to be more creative? Yes. And so typically I think this is, you can't tell, but if you go to like Gemini or chatgpt.com, whatever, like they'll have it set to maybe 0.6 or 1, somewhere around there, depending on kind of what the range is, to give you like something in the middle. Okay, something else is thinking mode. So if I ask this model, like what is or let's see, how about how many R's are in strawberry? The word strawberry. This is something that models have failed at or were failing at for a while. So it says there are 3 R's in strawberry. So it just answered by doing its typical next token prediction, right? The whole system prompt invisibly, then these words, and then it generated that token, then ran the whole thing through with all that, and then generated this token, and then this token, and this token. Okay, great. Now, if I turn on thinking mode, it will like talk to itself as it's doing this, and that will often help it get a better answer. Oops, let me go delete this and delete this, and then run this from here. Okay, and so if I open this up, I can see that it actually thought to itself, I've got a straightforward question. The user wants to know how many R's are in strawberry. It's a quick count, no need for external tools. I can deliver the answer directly. And then it tells me there are 3 R's in strawberry. So thinking mode uses more tokens. It generates more tokens before it gets to the final answer. And it's effectively asking the model to think through its answer before returning it to the user. And this can often lead to better results. It's unclear why to people all the time. Maybe, to me anyway. Maybe some people know why it's better. But the idea of kind of like it's reasoning through things and trying to figure things out, and by generating all those extra tokens and then having all those extra tokens as context when it tries to come up with the actual answer helps. Something else that's important is grounding. So we talked about how these things here, I'm going to go open up a new chat and I'm going to paste in, did the Lions beat the Chiefs on Sunday? Now, remember, this thing ended its training in January. So if I run this right now, it's going to say the Lions did beat the Chiefs, but that game was on Thursday, September 7th, 2023. It was the opening game of the NFL season. That's not what I want, right? Like, I want to know about this last Sunday, a couple of days ago. So I'm going to turn on grounding with Google search, and I'm going to run this again. And so now this time, it's actually going to say, oh, okay, this is something that the user's asking about, something news or topical that it might have happened recently. I should go use Google search to validate this. And it's going to say, no, they didn't. The Chiefs beat the Lions 30-17. and it took place Sunday night, October 12th, which is all correct, actually. And so this is where grounding can help. The other thing to notice, and they don't have it listed kind of the same way they do here as they do with some other LLMs, but the notion of function calling or tools, where you can give the large language model tools, like let's say a tool that can read data from an Excel spreadsheet and write data to an Excel spreadsheet, or a tool that can do a web search, or a tool that can get the weather. And then you give it access to all these tools, or in this case, functions, and then it decides if it needs to use one of those tools to get an answer to a question or to perform a request, then it can actually use those tools. It can decide, and using this kind of function or tool specification, it can call that particular tool. Okay, the last thing here on this particular topic is, I think we covered all these except for that LLMs have no memory. So this one's kind of implicit in what we've been talking about, but like we look at a big long conversation with a chat, and it's not like it's remembering all that, and then you're typing in the next request, and then it knows and it kind of responds. Basically, every time you send a new request to the large language model, you're sending back that entire conversation, and it's doing the whole next token prediction on that entire conversation. So the system prompt plus that entire conversation. And so if my conversation has gotten to 500,000 tokens, like every time I type in a new request, it's basically sending system prompt plus those 500,000 tokens and doing the next token prediction on that whole giant mess of stuff to come up with the one next token, and then doing it on that whole new mess of stuff with that plus one token to get the next token, and over again. So, from an engineering point of view, you're like, this is all like incredibly, remarkably inefficient, but that is the way that these next token prediction systems work. They have no memory. They have no state. They don't know anything. They are basically next token prediction machines. Okay, with that, let's zoom out a bit. Now that we know how it works, we know the underpinnings of this next token prediction machine and the mathematical system, the neural network that enables it to work, and how that's all trained with pre-training and post-training and reinforcement learning, and then how we do inference on that to get the next token, and how the system prompt is injected beforehand, and all the different things we can do. So let's zoom out a little bit and talk a little bit about some of the implications of some of these things to keep in mind. So number one, bias, right? You may be thinking that like, okay, I'm getting some kind of objective truth out of these systems, but at every single stage of kind of how this model was created, somebody's point of view was injected into this. What data do you choose to train on? Like, do I train on Reddit? Do I train on 4chan? Do I train on Wikipedia? You're choosing the corpus that becomes the training data for this statistical model. And in doing so, you're deciding what's important and what's not. Let's say you decide that Reddit's important, and you put 5 copies of the Reddit data set into your pre-training data. Now you've given it 5 times more prominence. Its probability is 5 times higher than it should be. And all of a sudden, like, that is more important, and you've given it more authority. And you can easily do that when you're creating your pre-training data. The training data itself is going to have biases embedded in it, right? Like, society is inequitable. The internet is a reflection of society, is also inequitable. And so if I ask for things like productive professionals, am I just going to get images of white men? If I ask for people social services, am I just going to get images of people of color? And that's because like this content on the internet is inherently biased, and then we are replicating that bias through these systems. Data poisoning, this notion that you're hoovering up the entire internet to put into this model, and you're not you're not curating it anymore. There's too much to curate. How would you even curate it? So you're kind of hoovering up the entire thing, and that gives bad actors the opportunity to like put content out there in the world that then gets hoovered up and put into these models. Anthropic recently released a paper that showed that 250 documents in an LLM could poison that LLM. And basically they have the word pseudo here. And if you now saw the word pseudo in your LLM would start triggering gibberish. And so it was that easy to poison the model. But other like kind of less explicit ways of doing this would be like, I read a story about a moderator on a subreddit who was being kind of very viciously attacking one of the competitors from a business he owned, and just having article after article after article in that subreddit, and then that being pulled into the training data. Or recently there was an article about like how a bunch of queries that are related to like the war in Russia and Ukraine being directed to like Pravda content, whether that's real or not, who knows? But theoretically, it's totally possible, especially given this recent Anthropic paper. And then what's the model being taught during post-training, right? We talked about those hundreds of thousands of examples of like good quality interactions with assistants that humans were generating that were then being used to taught the model to be an assistant. And you can teach the model to do anything. You can teach it to be a helpful assistant, teach it to be an edgelord. You can teach it to like deny, science. You can teach it whatever you want. And so like this is another way that the model creators are biasing the systems. And then what's the system prompt? We also saw how that's getting injected kind of behind the scenes, and we don't know what actually is in that prompt a lot of the time. So bias all the way down in pre-training, post-training, inference, everywhere. There's bias built into these systems. One of the big things we've seen, all of us have seen, is that people's data is being used. Their writing, their art, their video, their music, being pulled in and absorbed and used without their consent or compensation to create simulations of their work, which if you're someone who depends on generating that work for your livelihood, all of a sudden is now directly threatening your livelihood. And, you're kind of wondering like, okay, there's copyright laws that are supposed to prevent this kind of thing. But here's kind of the train of thought that that seems to be happening, which is all the model providers are like, well, we need this in order to make our models better. We can't pay for it because then our businesses would not be viable. So we're just going to take it and we're going to use it. And we're going to do that because these things are going to bring about, they're going to solve cancer. They're going to bring about like healthcare is going to be a solved problem. Climate change is going to be a solved problem. Like these things are going to create nirvana. And by the way, we need to be the ones creating it, not these other companies or other countries, because we will be the benevolent stewards of this amazing technology that will change the world much more so than any of those other guys. And so that's kind of the logic train that's happening here. And it sucks, honestly, and so we need to figure out what to do about this, because the rights of people haven't been eliminated, and these companies are just taking it and using all this data. Anthropic recently signed an agreement to pay $1.5 billion out to authors whose copyrighted books they used as part of their training data, and hopefully we'll see more of that. Quantity versus quality in the pre-training step, right? Do you decide to just use Wikipedia and then you've got high quantity but not a whole lot of quality? Or do you choose to just use like everything you can find? It doesn't matter what the quality is. And then you're going to end up with like a lot of swampy data, right? The internet's full of garbage, full of horrific stuff. And you're just pulling all that in kind of indiscriminately and using it. And then we're running out of the internet, right? And so like, this is why you're seeing companies like signing deals with, the Atlantic and the New York Times and Reddit in order to get, to pay for access to that data, because those guys don't want them scraping it just on their own and taking it with no compensation anymore. So if we run out of internet, then like that one scaling law about data, like what happens to that? Does that scaling law all of a sudden just no longer relevant? Or there's this notion of synthetic data that the models can create data that they then train on the models. And so then it's like the snake eating its tail, right? There's open questions there. There was this phrase being thrown around called model collapse, that like when that happens, the quality is just going to get worse and worse and worse. The author, I think I may have mentioned this earlier, but the author Ted Chiang wrote a great article in the New Yorker called ChatGPT is a blurry JPEG of the web, right? It's not an exact copy of the web. It's like you only have 1% of the storage of the web. How would you save it? But you have unlimited compute. You do what ChatGPT does, which is you like the same thing our brains do. You take all that data in, you train a statistical model, you make, these weights and parameters, and you encode a copy of that data, a blurry JPEG of that data, into this neural network that you can then put back out, but you can't put back out an exact copy. But you can imagine if you've taken a blurry photocopy of something and then you blurry photocopy it again and again and again, eventually you're just going to end up with blur. And so who knows if synthetic data is going to work? That is beyond my pay grade. And then these data centers, right? There's like every day you're reading about new data centers being deals signed for. And these giant data centers are using land, they're using energy, they're using potable water, they're generating pollution and noise. They're not bringing like tons of jobs or economic development to the areas that they're being built. You can see just two headlines here. Google had to halt a data center in Chile over the power and the potable water demand. That's not in the headline. And then Elon Musk has like a bunch of turbines powering a data center in Memphis that are leading to hospitalizations, which is just bad. And then on the post-training side, I think there's some like great quotes in this Guardian article, like AI isn't magic, it's a pyramid scheme of human labor. We've talked about all the parts where humans are in this post-training system, generating those hundreds of thousands of examples in order to do stuff, or, creating the content for the reinforcement learning with human feedback to train models to then give feedback to the models. And so lots of work, poor pay, opacity around the work, all that kind of stuff. And then even more concerningly, you've got things like these stories here about OpenAI. So, we talked about how you're like hoovering up all the internet, including all the horrific stuff on the internet, and you're not curating it at input time. So that means the model's trained on it and can then generate all that horrific stuff. So then how do you deal with it at output time? Well, you can't have humans looking at all that output, right? That doesn't scale. So you have to train another neural network to sit there and watch the output before it gets to the human and say, oh, no, this is bad. We're going to cut it off and not let it get to the human who asked. But how do you train this neural network? That neural network needs to learn about all the horrific crap that's all out on the internet. And so you have to have a bunch of humans looking at that horrific stuff and labeling it. And as you can imagine, that takes a heavy toll on human workers. And they're not getting paid very much to do this. And this is all happening in kind of the global South as well. So just to keep in mind, again, there's like lots of, this isn't all just like magic technology and math. It's a lot of human involvement in these systems as well. Okay, some other things to remember about inference. When you're using various free plans from the paid closed source model providers, just know that your data may be used for training. Google Gemini, for using their free plan, your data can be used for training. The same thing with Mistral and potentially others. So just know that if you're doing things like summarizing web pages and asking for help writing certain things, it's probably fine. But if you're doing any processing of sensitive or private information, know that if you are using one of those models that can use your data for training, that it may potentially get added to the pre-training data set for the next round and then be put into the model and then made available to everyone. So be aware of that. Mostly when you're on a paid plan somewhere, they usually say that they won't use your data for training. That's what they state. Whether you believe that or not is completely up to you. But if you're not, then your data may be used for training. The second we talked about earlier, hallucinations. OpenAI recently released a paper basically saying, these things, because of the nature of the way these things work, there is no eliminating hallucinations. They are next token predictors that are based on a probability, and that probability is based on the statistics of the training data set. And that's pretty much it. And as with any probability, if something has a 1% chance, it still has a 1% chance of getting selected. So then all of a sudden you're off on some random side road, not where you thought you'd be. And that is hallucination. And that is a feature of the way this particular technology works. These things have become machines for creating disinformation at scale, right? Now you cannot believe any audio, video, image, or text. anywhere as being authentic or from a particular source, because it's so easy to create these things. I mean, we all saw like all the Sora 2 videos, and before that Veo or Veo 3, Midjourney, Nano Banana, all these various systems that are out there for creating content now that looks real, and looks so real that it's pretty much indistinguishable from that which isn't. So now the people trying to spread disinformation have these machines that can enable them to spew this stuff out at scale. The Jagged Frontier is a notion that a number of academics wrote up in a paper, which is basically that, with a lot of our tools, there's very clear lines, right? Google Sheets is good for processing numbers. Google Docs is good for processing words. And I use one for one and the other for the other. And it's like a very clear mental line about what things are good at. But, with people, we have less good lines, right? I've got a new colleague. Do I know that he's like really good at math and like really not so good at English? I don't know these things until I start working with them. And it's the same with LLMs. They have this kind of thing called the Jagged Frontier. There are things that you would expect this kind of feeling like magical intelligence to be able to do that it can't. And then there are things that you're amazed that it can do. And you're shocked and surprised by it. So let's take a look and see kind of what your intuition tells you about some examples, and we'll try some things out. Can it summarize a web page? So here, I'm going to go to this web page. This is an article about AlexNet, and I'm going to use Ask Steve. Ask Steve gives you these one-click AI buttons. And when I press the Summarize This button, it's going to take all the text on this web page and send it in a prompt that says, summarize this in 5 bullets, and that's in less than 250 words. And here is all the text. So now we go back to like how all this stuff works. Basically, all that text gets sent to the next token prediction machine, and it reads all that, and then it predicts the next token. And over the course of its training data, it has, I'm sure, seen lots of examples of full articles or full white papers or PDFs, and then the abstracts or the summaries. And so it kind of understands this concept of summarization. So theoretically, this should be pretty straightforward. So I'm going to press the button, and it's going to run right here. And I can see that it just gave me really quickly a 5 bullet point summary of this particular article. And it's pretty good. Like if you actually read the article, it's pretty good. Now, there's definitely a kind of a conceptual difference between summarization and shortening, right? I think this is more like shortening. It went through and identified kind of the key words and kind of shortened everything and made it smaller, whereas summarization would indicate kind of some understanding of the particular concept that you're trying to summarize. But this seemed like a pretty straightforward one. Temperature set to 0, so always picking like the next highest probability token, and you get a pretty good summary by doing this. And so you can do this on any web page. Now let's look at the next one here. Can it count how many R's are in strawberry? We talked about that one earlier. If you try this on an LLM today, you will get varying results. They've kind of mostly fixed this, but sometimes you'll still get 2 or some other number instead of 3. But if you do a quick search, you'll see that like for a while here, this was all over that like AI didn't know how to answer this particular question. And then can it count the number of banks in each state? Okay, so I'm going to go to a web page, and it's going to have this number of banks. I counted in advance for us. 7 from Alabama, 4 from Arkansas, 16 from Arizona, 23 from California. So now let's go to this web page. And so we can see here, I've got 50 items on this page. It's a list of banks, and it's sorted by state here. So I've got 1, 2, 3, 4, 5, 6, 7 from Alabama, 4 from Arkansas, just like I said, 16 from Arizona, 23 from California. So now let's go into the chat here, and let's ask and say, I'm going to chat with this tab, and I'm going to say, let's see, how many banks are in each state? Also give me the total. Okay. And so what did it do? 7 banks in Alabama, that's right. 4 in Arkansas, 12 in Arizona, that's wrong, 16, and 23, or it says 19 in California, but there's supposed to be 23, for a total of 42 banks. So it just totally got this wrong. And if I try to run this again, maybe I'll get the same answer, maybe I won't. I don't know. Oh yeah, okay, I got I think the same answer this time. But it's wrong. And so you can imagine that like I'm coming along here and I'm doing my work and I think LLMs are amazing. And I'm like, oh, give me a chart of this. And I say, chart the number of banks in each state and include the number on the bar. And then I'm going to hit OK. And so now it's going to give me this really nice chart of all this data, but that chart is going to be wrong, right? These numbers are just wrong. So counting is something that LLMs are not very good at, which is surprising, right? Like you're sitting there going like, oh my gosh, they can do all this amazing stuff, but then they can't count. So don't count on it. Don't count on it to count things for you. This is another good example. Can it capture college data from a web page? So here, what I've got is I have this spreadsheet. My oldest son is a high school senior. He was trying to assemble all his prospective colleges into a sheet that would let him then filter down and figure out which college he wanted to go to. And so we built the sheet based on niche.com's website and kind of all the different fields that they have there. And so you can see I've got like the URL, the city, state, their overall grade, star rating, like lots of fields, right? That was all on that main niche.com page here. And if you wanted to copy and paste all that stuff by hand, it would take you like an hour. Maybe not an hour, but like let's call it half an hour per school or something ridiculous. A lot of manual work with like a lot of opportunity for error. Now, what I want to do is I want to have an LLM read this web page, extract these fields, and then I'm going to ask Steve to write it into the spreadsheet directly so I don't have to. Now, do we think it can do that? And so once again, what's getting sent to the LLM is a prompt that says, in this case, the prompt, let's go take a look at it. The prompt says, convert the provided text into an array of these entity objects. Here are all the properties I want you to get. And here's kind of the, if it's multiple choice, here are the choices, et cetera, and then here are all the fields and in the format that I want them. So you're giving a very detailed prompt saying exactly what you want. And now you're telling the LLM to go through and basically extract what is the acceptance rate? What is the net price per year? What is the number of undergrad students, et cetera. So I think it should be able to do this. It should be pretty good. And so if we go ahead and let's see, we'll run this. So our spreadsheet has nothing in it right now. Let me go press the button here. And what it's going to do is you can see it's going through and reading and extracting all those pieces of information. And then it just wrote it into the Google Sheet for me. And it did, in fact, get everything. It saved me a bunch of time. So that's another example. Again, temperature 0, don't hallucinate. Always pick the most probable option and put it in. Even then, there's still a risk that something went wrong. And you should always review this content, but it works. And so that's another one that you're kind of like, when at first I saw that working, I was like, my head exploded. I was like, wow, I can do that. It can save me a ton of time. This is another example from Carpathy. Can it print back the following string, but only print every third character, starting with the first one? So the word is ubiquitous. And so it should give me back starting with the first letter, U, and then every third character, Q, T, S. So it should be U, Q, T, S. So let's see, I'm going to copy this here, and I'm going to ask it, let's clear out the chat, and I'm going to just have it ignore the current page, and I'm going to say, go ahead and do exactly that. And what did it give me? UIUO. So that is very clearly wrong. So spelling is another thing that LLMs are not so good at. And then, can it get me a gold medal on the International Math Olympiad? Yeah. So apparently Gemini did this, and then officially, and then OpenAI did it unofficially. And then, can it tell me what is bigger, 9.11, 9.11, or 9.9? And so again, here's another Google search. This again, if you try it yourself, you'll see that sometimes it works, sometimes it doesn't. But you can see that for a while, the models were all failing on this and saying 9.11 was bigger than 9.9. This is now mostly fixed if you try it out. Okay, Copilot in Excel. So Microsoft recently announced an agent mode for Copilot in Excel. And then they published this pretty bar graph that shows the accuracy results on some tests. I don't know what this test measures, but I assume like how good you are at working with spreadsheets or how accurate you are. And it's 57.2%. And I honestly find this a little shocking that like, little more than half the time, this thing is going to get something right when it's working on an Excel spreadsheet, which seems insane to me. Like an Excel spreadsheet is someplace where you absolutely want to have the right data. Like this, especially if it's anything like you're doing for your business, right? Or for a school project or whatever. Like your data gets wrong, like the whole thing is messed up, right? Why would you ever trust this kind of thing? And in fact, who knows if this is real or not? I mean, as seen on Twitter. But you see this guy put these numbers in the column 1, 2, 3, and then in the fourth row put like, okay, Copilot, sum the numbers above, and it came up with 15. It's like, why would you ever use this in Excel of all places, or Sheets? Like to do this kind of work, I think you got to be very trusting if you're going to do that. The other thing is this notion of Workslop. This just came out, article from Harvard Business Review, basically about how AI content is destroying productivity, right? And largely it's because people are using this stuff to create substandard, subpar work, and then sending it down the pipeline to their colleagues, whoever, who then have to like undo it, redo it, or ask for it again. And basically it's making like even more work happen instead of actually saving time. And then there was this great report, again, in The Guardian, about how Deloitte used Gen AI to make some report that they were charging a lot of money for. And it had like all these errors in it because clearly they didn't check it by hand or with a human. So again, perfect example of Workslop here. And then this happened while I was at Google. I think it was in 2022. Blake Lemoine was an engineer working at Google, and he started believing that, I think it was Lambda was the model at the time internally, was sentient. And he kind of went on the news and started talking all about this stuff. So these things have kind of, because of their grasp of language, they have kind of hacked our brains into thinking that there's more there than there isn't. These are all recent headlines, right, which are just incredibly sad about the effects of chatting with an LLM and what that can do to people. And then this, I don't know if I have a strong opinion about, but I do think it's something to keep an eye on, to be concerned about, that people are establishing these romantic relationships with these bots. And I really loved this quote. This is from an article that talked about Blake Lemoine. "We now have machines that can mindlessly generate words, but we haven't learned how to stop imagining a mind behind them," by Emily Bender. I thought that was a really great, insightful quote. So what's next? What should you be kind of keeping your eyes on? Well, number one, like we've talked about how you can tokenize language. And what is language? I mean, music is a language, DNA is a language, audio is a language, video, anything that can be represented as like a sequence of symbols can be tokenized. And then you can use these next token predictors to try to create new things. So there's all sorts of opportunity in all sorts of different areas, like drug discovery, DNA, like all sorts of things. And so super interesting to see what's going to potentially happen there. There's this notion of agents now. And so, a lot of times you'll use an agent as part of a workflow. And I wouldn't even make all these LLM steps. I would make, some of them are just like deterministic steps. So let's give an example. You have a bunch of customer complaints coming in about your product, and you want those complaints categorized in one of 5 categories. How would you do it? Well, do you want to have a human sitting there and like categorize them all, or could you have an LLM? So you've got this like this workflow, and the first workflow is, take the next complaint out of the queue. The second step in the workflow is give it to an LLM and tell it to assign it to one of these 5 categories. And then the third step in the thing is, okay, throw it into the queue for the proper business. So that's a workflow that has an LLM as a stage in a workflow, doing a step that quite honestly would have been impossible to do, or almost impossible to do with technology in the past, or to do it well, and that you probably would have wanted a human for. But now an LLM could do it. It's being the simulated human in this particular workflow, which enables it to scale. The kind of second mode of running is the agent. And this is where the agent decides what to do. So in this workflow, you have an end. Like you've got a series of steps. You've defined that series of steps and when the workflow ends. With the agent methodology, you're basically giving the agent an open-ended problem and saying, solve this thing. And then it decides, what are the steps I need to take? What are the tools I need to use? Let me just keep going and going and going and going until I decide to stop. And so that's the key difference there. And that's what a lot of people are thinking the future is. And this is more like autonomy, right? You're giving the LLM more responsibility and authority and autonomy to go do the things it needs to do, but you're also giving it a ton more trust that it will do the things and it won't get stuck in an infinite loop. And so we're in early days of agents right now. And so this is a good kind of breakdown about like, okay, they're both going to make lots of LLM calls, but with an agent, the LLM decides when to stop. And with the workflow, it's predetermined. And with the workflow, it's good when you know the path you want to go on. And the agent is good when you're either too lazy to build that path and hope that the agent can do it for you, or you don't know what that particular path will be for that particular problem. And then where's all this headed? So right now we have ANI, artificial narrow intelligence, right? Or we're heading towards that in a bunch of different areas, which is better than human in a specific task, like, you know, the Waymo cars and autonomous driving. But all the frontier labs, all the big companies, whether it's, you know, DeepMind at Google or Anthropic or OpenAI, they're all trying to get to the right side here, or the center, AGI and ASI. So artificial general intelligence, this is like the pinnacle of artificial intelligence, you know, research and development. And what the way OpenAI describes it is highly autonomous systems that can outperform humans at most economically valuable work, or more simply, capable like humans in every task. But then artificial super intelligence, which is even better than humans in every task. And the big question is this the right path? There are lots of different branches of AI, of which generative AI came out and has like sucked all the oxygen out of the room and is kind of the primary path that's being pursued to AGI right now, this next token prediction machine. And the question is whether that actually will get us here or not. It's unclear. And if you like look at what the various academics and the people at these leading labs are saying, you have people on both sides. Some saying that this is a dead end and will never get us there, and some people saying that we're on the path and, you know, they've already seen signs of it. It almost seems like if we go back to the very beginning, the early days of AI, kind of the symbolic stuff, like I know about these things and the relationships between things, and then this learning stuff, it seems like the ideal is some combination of both, right? Is what you want. But I don't know. That's all above my head. So with that, I'm going to end here. I hope this has been useful to you. It's all been presented very confidently and potentially wrongly, just like an LLM. But I will trust you to verify my work. I put links to all the sources in the speaker notes if they're not on the slides already. And let me end with a couple of questions. And these are all things that people have claimed that AI will do, that generative AI will do. It'll solve climate change, enable affordable healthcare, provide equitable education, take all our jobs, lead us to AGI, go rogue and turn us all into paperclips. And then there's questions about how should Gen AI be used in education? Should it be regulated? Like all these kinds of things are open. Now that I've taken, 40 to 50 minutes and shoved a bunch of tokens into your training data of a brain, like let it all marinate and sift in there. And, I'm super curious to hear what you think of all this. Is this next token prediction machine going to do all these particular things? This presentation was fun to make. So thanks again to the Office of Entrepreneurship and Innovation at the University of Arkansas for asking me to give this talk. And I hope you found it useful. And if you did, please feel free to share it with somebody else. Thanks so much.